Hi, my name is Mike Rudolph, Aerospace and Defense Industry Manager at MathWorks, and today we're going to talk about the development of cognitive RF systems with MATLAB and Simulink. As you're probably well aware, this topic is something that could take several hours to present, and so given the broad set of interests within this field, I plan on giving a high-level overview in several areas here where you might find valuable, starting with a brief discussion for how digital engineering helps teams to collaborate. And then I'll discuss modeling and simulation at multiple abstraction levels and varying degrees of fidelity to generate data sets for these systems. We'll then show how you can make some high fidelity multifunction models. And then we'll end with some AI workflows that you can use to help apply to these data sets. Okay, so first let's talk about digital engineering. Electromagnetic Spectrum Operations, or EMSO, span multiple engineering domains. A typical radar or EW system might consist of the blocks shown here, whether it's the antenna and RF subsystems, signal processing, data processing, or the resource management and control. The cognitive RF systems that leverage AI across these areas are going to be needed to deal with increasingly congested, contested, and complex RF environments that we hear about so often. The data processing includes electromagnetic support systems that perform various data processing for things like situational awareness, spectrum sensing, RF fingerprinting, and anomaly detection. This could feed into the resource manager for a multifunction or multimodal RF system that schedules functions or modes or performs quality of service optimization between those different functions. AI can even be used for beamforming or digital predistortion techniques. And for folks working in defense applications like electromagnetic warfare, techniques place emphasis on these various subsystems in different ways. So similarly, cognitive RF systems will leverage various combinations of AI and apply them to these subsystems accordingly. The reality is that modeling and simulation needs are really going to vary based on multiple different factors, whether it's the area of focus like we just talked about, the type of scenario or the frame of reference that's being simulated, even the phase of the development life cycle, whether you're working on requirements or architecture all the way through the testing and validation and verification. You may have seen variations of the DevOps infinity diagram or the DevSecOps workflow, which is an increasing focus for the DoD in the US. And this illustrates an iterative process and continuous flow from the development and the design to operations and back again. Typically, DevOps has been used for software systems where continuous integration and continuous delivery mechanisms are going to be used to provide things like over-the-air updates to software that may already be in use. And then information on how that software is being used, such as new operational data or even errors that the end user might be seeing, those are continuously fed back into the development loop. The model that's used under the hood or through development might be physics-based, it could be data-driven, it could be AI-based, or some combination of these, depending on what you have available and if you're using it properly. With digital engineering, model integration happens throughout the program lifecycle. So combining digital engineering and DevOps, because the model is used and updated throughout that program lifecycle, it can really help to strengthen the collaboration across organizations, from universities or between organizations like universities, government labs, industry, and ultimately operational users and back again. The reason I bring all of this up is because our goal is to make MATLAB and Simulink the preferred platforms to develop these RF systems, from the analysis of real data to using more simulations for the design, deployment, integration, and even testing of these systems. And because no model is perfect, particularly because traditional approaches are limited to known emitters, and today's environment is so rapidly changing, and given how many unknown or unobservable factors may be at play for the systems you're developing, cognitive RF system designers are likely going to want to be able to rapidly iterate and update their models as quickly as possible to be able to deploy these updates to the field as soon as possible. And the reality is, regardless of whether you need a large amount of data or a reasonably small amount of data, if you have particularly if you have a good physics-based model and it's high quality. But either way, It's the speed with which your system can go through this cycle to update your models and back again to deploying to the field. The speed with which you can go through that cycle is likely going to dictate who's successful out in the real world. Models that you build up really need to account for a range of environments and scenarios. Revisiting this diagram that we introduced before, these subsystems make up things for subsystems of radar, comms, or other multifunction systems, which you might have many detailed aspects of the design that need to be considered here. For example, you have things like hardware gains and losses, operating parameters, processing and scanning techniques, the design choices and parameters that can feed into a cognitive radio's OODA loop. But equally important are the target and environmental parameters that are external to the system under development. You have variables like surface clutter and atmospheric conditions at the deployment site that need to be considered when you're selecting the system level design parameters or the control parameters for that cognitive RF system. Collectively, these combine in various ways to create an extremely large parameter space and variables that would feed into a scenario to be able to develop or even evaluate system performance against in the real world. Depending on what your team's trying to do, folks use various combinations of MathWorks products that support their end-to-end system design workflows, whether you're modeling commercial or standards-based systems, modeling scenarios, performing end-to-end system simulation, doing behavioral modeling, testing and deploying the prototype, or even fielded hardware. While MathWorks doesn't make any specific defense products, you might use this as a guide to see what you might want to check out to help save you time or increase your collaboration opportunities across your specific program or your team. On top of those tools, MathWorks supports a growing number of use cases and applications for AI in RF systems. If you have an interdisciplinary team that wants to leverage AI, we support this entire workflow from the data preparation, whether it's MATLAB or Signal Processing Toolbox, which has tools like the Signal Labeler app, the AI modeling with tools for things like machine learning, deep learning, and reinforcement learning. These ultimately can tie into the system design workflows like we talked about on the previous slide, and these could also be used in the data preparation phase as well. And then you have deployment to the fielded system through automatic code generation. So next, let's talk about modeling and simulation at multiple abstraction levels and what that means. I like to think about modeling and simulation from a mission engineering perspective, where the aggregation and the scope have a corresponding change in the level of fidelity as you go up and down this pyramid here. At the component level, for example, engineers and scientists might be developing something like antennas or phased arrays for a wireless comms system. At the system level, you have systems engineers and maybe even managers that might be interested in that system level performance in terms of specifications measured against a set of requirements that maybe your customer or your team has set for your group. And this could be physical specifications or even performance specifications. And that might connect into a system of systems level within mission engineering context. And this area might not yet have specific requirements that you have for a complex system of systems, because it's not really realistic to develop those requirements until more is known about what's possible. And so asking questions like, how does this fit in and connect to the bigger picture, and what are the different trade-offs that I might want to consider if I do connect it here? And then, of course, there's the mission level, which ultimately is the most important driving force in this picture. The digital engineering vision is to help stakeholders here get answers to questions like, how does swapping this component for another impact the mission objectives? Or where can my area of operation extend? And testing it out on a digital model in a digital scenario before moving out to expensive or long lead time equipment or deploying it to the field. So answering the questions like this with a reasonable degree of confidence with models at the foundation built up using digital engineering is where mission engineering has the potential to be the most valuable. I'll discuss how MathWorks products can help connect stakeholders across all levels through varying degrees of levels of fidelity. It's important to remember here for multifunction systems and modeling across different abstraction levels, just how many tests you might need to do at each level. Realize you might need tens of thousands of tests at the bottom, maybe only a handful at the top, but ultimately you need all of this to test cognitive systems. Doing just one mission is fine for potentially fine for traditional systems, but not necessarily for a cognitive system. And this is really important because depending on the question that you're trying to answer or the system that you're developing, you want to be able to model really what's necessary and only what's necessary. Otherwise, you risk wasting time and resources through modeling and simulation, especially if you're running thousands and thousands of simulations. So let's consider the level of abstraction within our models that you might use for various components of those models. And so this could be through something like power level analysis, which is based on either simple or sophisticated link budget analyses to determine metrics like SNR versus range, for example. And this is usually performed maybe early in the program or just prior to deployment to evaluate various trade-offs to make sure something's going to work the way you expect it to. And then you have measurement level models that incorporate sensor statistics to generate detections or clusters or tracks. And you can use this to evaluate system or even systems of system performance. Maybe as the project progresses, or if you're working on algorithms, it might be necessary to increase the level of model fidelity, moving from the statistical level to the signal level simulation. And here, high fidelity signal levels can generate raw IQ signals that can be used in the development of those algorithms. The length of a scenario can really dictate which modeling abstraction level makes sense. For example, for longer scenario times, like seconds, minutes, or longer, it might be better to generate statistical or probabilistic radar detections and their tracks to cover a more complex scenario or to test tracking or sensor fusion algorithms. But higher fidelity physics-based simulations that include RF components, transmitted waveforms, and signals at the receive array, those are going to be needed for events of interest or during development of signal processing algorithms. The higher fidelity simulations can also take into account the detailed designs for the antenna array and RF subsystems. And that can feed the other way where lessons learned at that higher fidelity might help to improve the quality of the reduced order models that you can use at the mission level. Each one of these might feed into its own appropriate AI model, and MATLAB and Simulink can provide you with the ability, in many cases, to transition between these levels that we'll talk about in a little bit. So being able to interactively design and evaluate radar systems. At the power level for modeling of a system, for example, you might be looking to do link budget analyses, and you're probably doing that using a spreadsheet, and you can definitely use it with the radar toolbox shown here, where you can interactively design and evaluate these radar systems. And using various threshold and objective metrics, you can evaluate the system's design against some high-level requirements. And so for the increased fidelity that you might want in that link budget analysis for what you're trying to design, the radar toolbox has features to incorporate things like environmental effects due to Earth's curvature, atmospheric, terrain, and precipitation. You could add custom radar cross-sections, antenna or array models, and both range-independent or range-dependent losses. And those are all included here out of the box. And from there, you can generate metrics as well as save or export these results and continue your analysis elsewhere, or run simulations that leverage statistical models or share this information with collaborators to leverage some of the outputs here as well. For the measurement level, right, we can model systems and system of systems using this level of fidelity. As I mentioned, these are statistical as opposed to signal level models, which would produce time series data, which we'll talk about soon. The same scenario can be used to generate data across these abstraction levels, depending on what's needed. There are several examples that we can go over and ship with some of our products like Radar Toolbox that we can go into if you're interested, but I'm not going to cover them in this session here. In radar or EW or comms systems, there are many different control parameters that a cognitive RF system would need to adjust to be able to respond to a given scenario. And there are just as many parameters that can be adjusted to generate representative data for the scenario itself. For example, you have platforms and targets that you might want to model. There's surfaces and clutter that you'd want to take into account, the trajectories of the nodes that are in the scenario, sensor models, and from here you can then generate data sets that can be used for further analysis or the training and testing of an AI model when you're simulating these scenarios collectively. For platforms and targets, these can actually be modeled across a range of fidelities as well. This includes point targets, which can leverage arbitrary radar cross-section patterns. You can use cuboid shapes and the analytic results that come from those. Multi-scatterers that leverage superposition, and this could include things like microdoppler effects on things like airborne platforms. Or you can run an EM solver on any arbitrary shape that might be defined in STL files mesh. And all of these, or even your own measurements, can then be fed back into a radar cross-section for modeling and simulation. It's important to remember the saying here that all models are wrong, but some are useful. This is where iteration using something like the DevOps methodology we talked about can help you to build confidence in your model as you continuously improve them throughout the cycle. So start high level and add fidelity over time. Using a common scenario that adds fidelity across abstraction levels also provides you with a pretty powerful collaboration environment as you transition between them. For instance, going from surface models to the radar surface return on land and sea-based surfaces and clutter that are included out of the box with Radar Toolbox. For example, here we show how to simulate a PPI radar image for a rotating antenna array in a maritime environment. So you can configure a radar scenario like the one shown on the left here, add spectral sea surface models. You can emulate an extended target like a surface vessel with a collection of point scatterers. Then you can generate the return signals and plot the PPI image of the result. And then you can even use this to apply AI techniques to automatically reject the clutter in that model that's shown on the right here. So next we'll discuss how the signal level model abstraction level can be applied to RF emitters, targets, as well as interference sources. Even within this abstraction level, probably not surprisingly, the waveform models can be created with varying degrees of fidelity and detail. So in this section, I'll show just a few examples of what you can do. Similarly to the land and sea versions of the figure here, for surface and clutter modeling, you can do things like generate IQ from the custom surface reflectivity maps, whether it's random or real-world based. And this can be used, for example, with synthetic aperture radar system-level scenario models, all the way down to the raw IQs to test raw IQ signals to test your processing algorithms. For channel modeling, some amount of propagation modeling is going to be important in many, if not most, RF modeling scenarios. This is a list of various channel models you might consider depending on your application, like wireless comms or radar. And we're interested in hearing about your needs beyond this, so please let us know if you have specific needs here that aren't covered through our products. This can also include RF component or subsystem designs. So if you want to include signal level models of RF components or subsystems to include effects like IQ imbalance or amplifier noise and non-linearities or frequency offset, you can certainly include those here. Or there's techniques to develop ways to compensate for those effects. You can even create RF subsystem models from real system specs, which can help you create data sets that add realistic distortion. And this can help with things like RF fingerprinting, or otherwise known as specific emitter identification techniques. Or you can even test out how a new technique might work on a hardware model that leverages these parameters. You can even build an interference model and test the mitigation techniques within the same design. On a physics-based transceiver, which includes a number of parameters like the ones listed here, you can apply space-time adaptive processing, shown in the example here, where when enabled, it actually forms nulls toward the clutter and a jammer to suppress them. And this allows the system to better detect a target of interest. You can model that congested, contested, and complex RF environment by adding interfering emitters using standards-based or custom waveforms using a number of different apps like the wireless waveform generator. You can do this programmatically, or you can do this through data replay from data you collect over the air. And I do just want to note at this point that while we do have full support for commercial standards like 5G, LTE, commercial SATCOM standards, and several common radar waveforms, as well as any custom waveform you'd like, really, MathWorks does not generate military standard waveforms out of the box. Here's an EW example that uses the phased array system toolbox. This example simulates a scenario with a ground surveillance radar and an airplane that has a radar warning receiver mounted on it, which is a passive electronic support system. The radar warning receiver detects the radar signal, and then it extracts various waveform parameters from the intercepted signal using signal and image processing techniques. These are the kinds of parameters that are used in the pulse descriptor words that are used elsewhere in cognitive and other RF systems. And you can use it in things like classification workflows, or even feed that back into a detector to estimate your emitter location like we're doing here. So next I'll briefly discuss some adaptive examples that could be used as behavioral models of the operational environment, or you can even use these as building blocks or inspiration for your own cognitive solutions. So adaptivity and mode agility can be time-based, it can be spatial, or it can be frequency-based. So whether it's something like PRF agility, frequency or waveform agility, or even beam steering, these can all be modeled. So I'll go through some examples here. So this shows a radar that's actually changing its PRF based on the detected range of a target. It starts out searching at a 5-kilometer range, but if the radar detects a signal within 2 kilometers, then it switches to a higher PRF, which has it only looking for targets within 2 kilometers, which improves its ability to detect higher speed targets closer in. So behavioral models like this could be used for generating training data sets depending on what you know about the environment you're going to be going into. Frequency agility for interference mitigation. This creates a scenario with a ground-based radar and an approaching aircraft that can emit interfering signals. So here, frequency hopping allows the ground-based system to mitigate interference from an airborne target's spoofing signal. So when the switch is flipped, you can actually see the desired signal appear in the second frequency band that we're showing in the bottom plot here. A more complex model might be used for something like reinforcement learning to perform frequency agility on the fly in a cognitive system in a closed loop fashion. Any number of waveforms can be generated in MATLAB and Simulink and saved to a library and even indexed as needed, or fed state information about this scenario that you're operating within. So depending on what's happening in your scenario, that can drive the choice of waveform that you're using by your system. Next generation 6G and cognitive RF systems, however, these are going to likely aim to generate waveforms on the fly. So a next step here might be to replace this block that we're showing with something like a deep learning model that does just that. So regarding AI workflow, as I mentioned in the previous section, these were actually merely adaptive examples. So there are a number of AI techniques that would need to be applied to be considered a cognitive system in order to be even more flexible and responsive to its environment. So the techniques described earlier can certainly be used to create data sets to train an AI model itself or to test that model that's already been created. I will give a very high-level overview of the AI workflow that these data sets could feed into to give you a sense for what you might use in your development for these cognitive systems. And so for instance, the questions of generating data sets for those AI models, for instance, the waveform modulation classifier, the waveform or signal level models can be really valuable to generate these representative data sets for training. If people are interested, we can provide sessions for your organization on AI for radar and comms, expanding on a growing number of examples like the target classification, emitter identification, anomaly detection, antenna RF, and an increasing number that are increasingly growing. And so cognitive systems might use these and more in a closed loop fashion to be able to respond to a given scenario. But these might provide you with a good starting point, especially because the code for these examples is provided to you. They can be combined, configured, parameterized to create many different possible data sets and combinations of these to use many different possible solutions. So with regard to AI-driven system design, one thing to remember is that a lot of discussions around AI are usually talk about deep learning, focus on the development of the predictive models themselves. But really the end-to-end workflow that includes the data synthesis and augmentation, the labeling, the pre-processing, and the deployment are all equally important. So keeping this workflow as a reference, let's quickly go through some of the key challenges before we dive into each one of these areas. Now, hopefully it's clear that you're not going to get a good model without good data to train it on, and that's even more true for signal and time series data. So some work may be needed in these initial steps of the workflow. So to train a deep neural network in particular, sometimes a large quality data set really is needed. And not only that, supervised learning approaches require labeled data sets. Labeling, it's a very repetitive, very time-consuming task, but it's an essential part of the workflow. On top of that, radar and wireless specific expertise and tools can play a key role when you're preparing and pre-processing data to train these networks, especially because you might not find quite as much published research in these application areas as you might for applications based in computer vision. So I hope the workflows that we discussed earlier can help you with developing and doing your data preparation there. Once you have your model ready and want to deploy it, it's also often a challenge to write the C or C++ or CUDA code for targeting hardware platforms or to deploy to the cloud. And with digital engineering using MATLAB and Simulink, keeping your model as the source of truth, we make it easier for you to be able to deploy to a range of different architectures. So let's walk through the various parts of this workflow and end with a brief example of how this can be applied with your team's infrastructure. So with regard to data preparation, this really helps to build the better AI models overall. The pre-processing helps to ensure that you have good quality data, which means less data may be required to train the AI model. And this can provide you with insights and help to simplify the network architecture, that help to simplify the feature extraction, and ultimately helps to improve the performance. So this is a critical part of the workflow here. You can acquire data directly into MATLAB using lab hardware or software-defined radios. In addition to working with recorded over-the-air data, you can also synthesize labeled wireless and radar data for cognitive radio applications. Teams even build up hybrid data sets that augment recorded data with synthetic data that might not be available over the air or easy to collect over the air. Of course, it's easy to label the data that you synthesize, but in the real world, things are really messy. So if you're using recorded data, you can use our Signal Labeler app to help automatically label or reduce the typically time-intensive step of labeling. You might also want to use this part of the workflow to answer questions like whether or not the pulse descriptor word that you've extracted is going to be useful to describe a system that maybe you haven't seen before. So with regard to AI modeling, let's move on to the second step here, one that perhaps gets the most attention. And within the MATLAB environment, you have direct access to common algorithms used for classification and prediction, from regression to deep networks and more. You can use pre-built models developed by the broader community. If you find a model on the web or receive a model from a colleague using a different framework, you can import it into MATLAB. MATLAB supports the ONNX format, which is a standard extension for deep learning models that you may be aware of. And then certainly examples, and this is one of our areas of value, right? Where these are the ways that engineers learn how to use algorithms, maybe find the best approach or something close enough to their specific problem that they can start from. As I mentioned, we provide a growing list of examples for AI, building on things like deep learning models in a wide range of domains. We have a whole set of talks on AI modeling if folks are interested, so please reach out if we can help you set up an info session to discuss any of these in depth. We talked a lot about simulation already, but by incorporating the given AI model into your broader system, there are several systems engineering and even verification and validation frameworks and tools that you can use to test and evaluate performance and even generate reports automatically through CI/CD and the DevSecOps workflow. So again, reach out here if you're interested in some of these tools and frameworks, and we're happy to chat. Once you're happy with your network design, then you can deploy it to your platform of choice. You have AI models that are in MATLAB and Simulink. You can deploy those to embedded devices, edge devices, enterprise systems, the cloud, or your desktop without having to rewrite significant portions of your original model. And so this is the beauty of digital engineering and the ultimate vision, where model reuse both throughout your program and even across programs can add tremendous value. So to summarize this workflow, I'm going to go through an example that shows how to train a deep learning model for a spectrum monitoring application. And one of the uses of spectrum monitoring is to characterize spectrum occupancy and then use that to understand how to respond to that scenario. The neural network in this example is trained to identify 5G, LTE, and radar signals in a wideband spectrogram. Following the workflow we talked about earlier, you can create a variety of signals that might either be synthetic, again, standards-based or custom proprietary waveforms, and using over-the-air or over-the-wire recordings to which you can add channel and RF impairments, as we discussed as well. Here we actually use a spectrogram as an input to this particular neural network. And if you have a lot of data, this is where you can use tools to help automatically label your data sets that you're recording over the air or over the wire, and as well as track the distribution of labels and track the progress as you build up that data set. Then you can design and train and modify the neural network itself using transfer learning from a pre-trained network. So here we're actually doing semantic segmentation and leveraging the ResNet 50 network to pick out those different waveform types. Next, you can test on additional synthetic or over-the-air signals to verify the performance or even decide if additional real or synthetic data are needed. And then finally, you can deploy to your hardware of choice. So this is just one of many applications of AI in this space. We have a growing number of examples, as I mentioned, that showcase workflows like this. This probably, for many people watching, isn't exactly what you're trying to do, but just I want to highlight the fact that there are end-to-end parts of this workflow that you need to consider. And depending on what you're trying to do, we're happy to provide you some guidance in terms of examples or workflows that might be most useful to your team. So I hope that this high-level overview gave you a sense for how you can leverage digital engineering and the data generation through modeling and simulation at various levels of fidelity with MATLAB and Simulink to help turn your adaptive and multifunction systems into cognitive radio and RF systems. Many of the examples that we showed here ship with some of the corresponding toolboxes I mentioned. You may have noticed a lot of example links throughout the presentation. You can try these out for yourself through free trial licenses, or better yet, they can be demoed in depth for your team by one of our application engineers. And please reach out if you'd like more information, and we'll be happy to get the conversation started.